So at the end of the period yesterday, we talked about how if I have a polynomial of nth degree, Chuck, nth degree, that I can have how many, at most, what's the ceiling for as many turning points I can have, or local maximum minimums collectively?
N minus 1.
Good job, Chuck! N minus 1.
There you go, geek.
Okay? So if I have like a fifth degree, the most you can have is 4, right? Now that's setting the ceiling, that's setting the height, okay? You can have less than that, and we'll talk about maybe some options of the less than that, because if I have a fifth degree, and I can only have 4 turning points, then having 3 might throw a wrench into things, might impact things negatively, okay? But I want to talk about why we only get n minus 1, okay? So I've got, let's see here, we've got this function here. I'm going to start with just the generic x cubed plus 4x squared plus 2x plus 3. We'll do 1 or 2 of these things. And we're interested right now in the turning points. That's a third degree polynomial, right? So at most you could have 2 turning points, correct? Okay. If you were to look at x to the third just by itself, just real quick, how many turning points does that have? Yeah. So turning points is a maximum. There are none, right? So that one, the 0 point is actually called an inflection point. Okay, where from the left of 0, the graph is kind of like concave down. To the right of it, you're like concave up. Okay, we'll talk about that later on. But the idea is if an x to the third, we got an example there where no turning points, no local maximum minimums. And then we got an example here where we have 2 maximum minimums. Okay? The argument is, can I have 1? The answer to that is no. If I have only 1 turning point, that thing's going to be like parabolic, right? It won't match up with the end behavior that it's supposed to have. Okay? So we'll talk about why eventually 1 kind of gets kicked out with the graph here a little bit. Okay. So that's what we get. All right? Now I want to talk about why is n minus 1? Why is n minus 1 the most turning points we can have? And the argument for that is because we're going to be looking at the derivative of this thing. Okay? And we talked about previously that the derivative of this is, I'm just going to show you the derivative here. All it did is it took this 3 that was right there in front of that x cubed, or behind the x cubed. We put it out in front through multiplication, and then we remove 1 from that x cubed. So it becomes x squared. We take this 2 that's behind the x and with the 4x squared. We multiply that out in front by the 4, get 8, and then subtract 1 from that power of 2, and gives 8x. You do the same thing here. There's a 1 right there behind that x. Multiply it out by the 2. Subtract 1 from that exponent of 1, and you get 0x to the 0, so that's just 2 then. So this is the derivative. Does that make sense? What that thing does is it gives me a formula to find the slope of that line at that value of a. Okay? So let's see if I can get a to be at like 3. Negative 3. This thing's touchy. Come on. There we go. Okay. Now if I were to round this to a couple decimal places, I'm really not at 3. Let's see if this will work. There we go. That looks better. Snap. There we go. Awesome. All right. So if I evaluate this thing at negative 3, okay? If I evaluate this thing at negative 3, I get negative 3 squared is 9 times 3 is 27, right? Plus a negative 24. What's 27 minus 24? 3 plus 2 is that 5 right there, right? Which that 5, okay, if I ask this to find the slope of this line right here, you see it's 5, right? Does that make sense? Okay. So the derivative is an algebraic tool to allow you to find the slope of that green curve anywhere that I want to. Okay. Now, let's think about this. Where does that slope which is this number right here, where does that slope start to become 0? Yeah, I'm going to stop there. That's close enough, right? Okay, that's pretty close to 0. Now, here's the thing. Where that thing is 0, okay, the derivative is this thing here. So that blue curve right here, when I set that thing equal to 0, set the blue curve equal to 0, it gives me these 2 points, D and E, right? Does that make sense? Set this equal to 0. Now, the ordered pair for D is negative 2.387. What do you notice the ordered pair for that maximum was? What was the X value? It's the same thing. Okay? So, the idea here is that if I want to find maximum and minimums, okay, algebraically, I have to find the derivative and then set the derivative equal to 0 and solve that equation. We have a 3x squared plus 8x plus 2 equals 0. We can solve that, probably using the quadratic formula, and it will give us negative 2.3874, and that will be the 0 of the derivative, but it then is a maximum of the original cubic. Does that make sense? Okay. Now, there's another one over here. Okay, as I move this tangent line, it's going to become 0 again, kind of right there. Let's move closer to 0. This thing's touchy. So close enough there. Okay, so if I find the ordered pair for E, you'll see that the X value of E is the same then. Now, there's a little bit of rounding here, but it's the same as the X coordinate of that minimum. Okay? Does this make sense? Yeah. All right. Now, when you get to calculus, we'll do this in calculus without a picture, without a graph. Okay? And we'll set up a chart, and it's called the first derivative test. So basically what you'll do is you'll find that blue derivative, algebraically, 3x squared plus 8x plus 2. You'll set that equal to 0. Now, eventually, depending on what the green function was, that f prime, that blue one, might become a cubic. It might become a quartic. And you have to factor. You have to do all of the work that we're about to do with dividing polynomials, the P over Q, rational root theorem, all that kind of stuff, with this to find these locations. Okay? So you'll do that. You'll set this equal to 0, solve it. Okay? You'll set up a number line. You'll put a point here at negative 2.387. You'll put a point at negative 0.2792. And then you're going to say, okay, I want to take a number. You guys remember doing sign charts? Yeah. You're going to take a number to the left of this. Okay? So maybe I take like negative 3. And I'm going to evaluate this function at negative 3. It gives me 5, right? Does that make sense? Then I'm going to go to the right of this point D and maybe try negative 2. So I'll try negative 2. And I'll evaluate, and so it'll give me a slope of negative 2. So I had a slope to the left of positive 5. And I had a slope to the right of negative 2. So what does that tell me my graph was doing? From the left-hand side, it was increasing here, right? Because it was positive. Slope was positive. To the left of it, the slope is decreasing. So if I go from a positive to a negative, somewhere in between there was a 0, and because it went positive to negative, that 0 must have been the highest point possible. Must have been the maximum. Does that make sense? Over here, when I start doing these over here towards this negative 0.27, what's the slope of that line? Is it positive or negative? It's negative. Once I get past that minimum, now the slope is positive. So when I transition from negative slopes to positive slopes, that transition, that intermediate value theorem tells us there's a zero there. That transition from negative to positive tells you at that point had to have been a minimum. Does that make sense? Okay. Those are things that are going to be talked about in greater detail in calculus, but my hope is that if that is your plan to get to calculus, to be efficient and effective in calculus, that you understand this stuff right now. Maybe not the calculus right now, but the things that we're going to be doing are going to be used heavily in calculus. So you're going engineering route, maybe business calc route. This stuff's going to be important. Okay. All right, I want to put one more in here. Let's see. X to the fifth plus 3x to the fourth. X to the fifth plus 3x to the fourth minus 5x cubed. Don't do that. Hold on a second. Let me write this down real quick. All right, so x to the fifth plus 3x to the fourth minus 5x cubed minus 15x squared plus 4x minus 15. All right. We'll zoom out. Let's look at this thing. I don't care about these zeros anymore, but look at that curve right there. Okay, it's x to the fifth. Let's change this to just that minus 15. Does everybody agree that that's going to slide this thing down 15 units? Yeah. Let's just make it minus 1. Bring it up a little bit better. And if I look at that thing, how many turning points do I have? 1, 2, 3, 4, right? Well, it's x to the fifth, so that's the maximum number of turning points I could have. But if I look at the derivative of that thing, is that turning point right there where my cursor is that the same position of an x-intercept of the blue? That make sense? Is this turning point right here the same as an x-intercept of the blue? This turning point right here is the same as an x-intercept of the blue. And then this turning point here is the same as that x-intercept of the blue. So the argument then is, if we are going to try to find the turning point of the maximum minimums of an x to the fifth like this, we need to be able to solve that blue one equal to 0. Well, if you think about trying to factor that blue one, we're going to have to use the techniques that we're about to learn to do that, which is the P over Q rational root theorem that you guys did a little bit with last year. Okay, maybe spent a couple days on it. But that ends up being something, guys, that is very prevalent and useful in a calculus course. Okay, and what stinks in a calculus course is that it doesn't tell you need to factor it. It doesn't tell you how to factor it. It doesn't tell you what tools that you have available to you to factor it. Okay, it just shows up in the implied concepts. If I know that the turning points occur at the zeros of the derivative, then what it means by the zeros of the derivative means I take the derivative, set it equal to 0, and solve it. And when it's the exponent is greater than 1, then I have to factor to do that. Okay, so that's kind of the trajectory that this stuff is going towards for calculus. All right. Yes.
So on the zeros, I was just graphing it because wherever was hard.
Yeah.
And I would click on the points, and for some of them, it would say root over the top of it, and then others it would not, and then others it would say like extranium, and I have no clue what any of that means. Does that matter at all?
Using GeoGebra.
Yeah.
So, when I click on a function, let's just work at this green one. Okay. If I click on the roots is equivalent to the 0. Okay? When I click extremum, that's the maximum minimums collectively. Now, it doesn't tell me which one's which, but that's what that means. And now, so here are my thoughts. Okay, we can kind of circumvent a lot of the information, a lot of this work, by using this to answer our homework questions. Right? My hope is that we're not doing that and kind of losing the opportunity to really learn this. Are we trying to get through the homework? Or are we trying to learn from the homework? Okay, so keep that in mind. Okay, so let's talk about some options for these things. So I'm going to start with x to the fourth. X to the fourth, we have, how many turning points am I allowed to have there with that first polynomial? Okay, so the most is 3. So let's draw one with 3. What's the end behavior going to be? If I go to positive 3, where's y going? Positive 3. So Blaze is giving me the touchdown, right? So that is my end behavior. Okay? Well, if I'm going to have 3 turning points, n minus 1, right? Well, that's your n. Then let's draw 3 of them. There's 1, there's 2, there's 3. Now, that thing doesn't have to touch the x-axis or all that kind of stuff. But would you agree that that's 3 turning points? Yeah. That models the end behavior. So awesome. That is a potential graph that we could have. Okay. Now, you're also going to see from time to time, maybe this thing comes way down here, goes up, comes back down a little bit, and then goes back up, right? So these kind of, these valleys here for these minimums don't have to be level with one another. Does that make sense? Okay. Can I have 2 turning points? Yeah? Okay, so here's 1. So I need another one, right? So another one, so we're going to need a maximum now, right? So if I have only 2, where's this thing going to keep going? Down. Negative 3. Does that match that end behavior? So I cannot have 2 turning points. Okay? Because the end behavior is not then matched. Can I have 1? If I have x to the 4th, doesn't x to the 4th look something like that? Okay. You can also graph one of these where, so let's say I have like x minus, let's go plus 4 cubed times x minus 3. If I FOIL that, will that be x to the 4th? So that means negative 4. That means negative 4 is going to have a cubic behavior, right? So negative 4 is actually going to look something like that. Does that make sense? At positive 3, we have a linear behavior, so it's going to look something like that. Well, the only way that I can do this is to go down and up through there. How many minimums do I have there? I just have 1 right there, right? This is an inflection point. Okay? What I mean by inflection point, I said that a couple times now, is that, and you'll talk about it with those derivative tests in calculus, but the way I always think about it, if I am to the left of this point, I kind of have a concave up kind of behavior here with that branch of the curve. To the right of that, I've kind of got concave down. Does that make sense? Okay. When that happens, that point in which that concavity changes is referred to as an inflection point. Okay, so we're allowed to have, so if n was 4, we're allowed to have n minus 1 turning points. Was I allowed to have n minus 2? No, because that would have been 3. Or, sorry, that would have been 2, right? And we said 2 couldn't happen. Was I allowed to have 1? Yes. Yes. Okay. So I was allowed to have 3 or 1. If I think about that, what that means is I could have something like that. N minus 1 minus 2. N minus 1 will give me a 3, right? Remove 2 from that, and I could have 1. Okay? Let's talk about a fifth degree real quick. Talk about a fifth degree, and we'll see if this pattern is maintained. If I have fifth degree, I could have how many turning points? 4. So there's 1, 2, 3, 4, right? Okay. So if n is equal to 5, n minus 1 equals 4 is okay. Can I have 3? Can I have 1, 2, 3?
No.
Can't have 3 because it's going to not model the behavior, right? Can I have 2?
Yeah.
Yeah, so let's talk about how the 2 would work here. If I had 2, so it'd be something like this, right? Okay, now it'd be a little bit different than that. The idea is if I'm going to have 2, it's got to be to the fifth, right? So it means I'm going to have 5 factors, right? So that produces a factor and that produces a factor. Okay? Well, one of those is going to have to be let's think about this. That's actually, I'm sorry, that's going to be a factor too. I didn't see that one. I didn't think about that one. So one of those is going to have a multiplicity that's different. Okay? This could be an odd multiplicity, and an odd multiplicity, all of 1. Well, that would be a degree 3, right? Does that make one of these then to be a degree 5? Doesn't one of these have to be a degree 3 multiplicity? Does that make sense? Is that 5 roots then? So this graph here would actually be more like kind of that, where we have that cubic behavior at that 0, but then up and down. So there's the 2 possible ones. Does that make sense? So you can have 2 extremas there. So we had n minus 1 was okay. We could have 4. We couldn't have 3, but we could have n minus 1 minus 2, which gave me 2, right? What about this? If I graph just x to the fifth all by itself, doesn't it look something like that? How many extrema do you have there? You have 0, right? Isn't that this number here minus 2? I go n minus 1 minus 2 minus 2. Kind of like that. Does it make sense? So, my hope is that you realize, you see the pattern here. N minus 1 sets your ceiling for the number of turning points you could have, right? You get that ceiling, and you could have 2 less than that. You get that amount, you could have 2 less than that. You get that amount, you have 2 less than that, until you get down to 0 or 1. Make sense? Obviously, we won't want to subtract 2 from 1 because it's going to be negative 1. In regards to counting things, finite things, you don't ever have a negative amount of finite things, right? So we don't want to go to the negative side. So we stop at 0 or 1. So if I told you have a 12th degree polynomial, n is equal to 12, give me the possible number of turning points this thing could have.
11.
Okay, 11, that's the max, right?
Yeah.
That's the maximum number. So what are my other options?
9.
9, 7, 5, 3, 1.
0.
Nope. Can't have 0.
Negative.
I just go down when I stop at either 0 or 1. If n is even, you'll stop at 1. If n is odd, you'll stop at 0.
What about negative?
Can't have negative because that's telling me how many of something I have. Okay? So I have 11 turning points. I can't have negative 1 turning point. That doesn't make sense. Is that okay? We understand that? Okay, so we're going to ask those types of questions on a test or quiz. I'm going to give you a polynomial like P1, P2, or P3 and say, okay, what is my maximum number of turning points? Answer that, and then the next question will be, okay, what are my options, though? If that's the maximum, what could the other things be? Could the other optional turning points be? All you got to do is subtract 2 from that max. Okay? All right, so as we look at these graphs, guys, and so this completes section 3.2. I want to start 3.3. and it's kind of continual. It doesn't really, like I said earlier, that we really don't need these section breaks in this chapter. But we're collecting data. We're collecting information about these polynomials so that we can graph them. Right now, we've determined end behavior. Okay? We've got the idea of what y-intercepts are. Those are really easy to find. We understand now potential amounts of turning points. Okay? We understand the zeros. Okay? Now, if we understand those things, let's see if we can determine those zeros. And that's the hard part, okay? Because everything we've seen so far, if I wanted you to graph something, it has been in this format right here. It's been in factored format, right? Well, a lot of times, they give me the problems, or we run into situations. I don't know where everything went. What the heck? All right. We run into situations where we end up with like polynomials like this, in this format. Okay? Where I want to know what the zeros are, they're not explicit. They've already been kind of foiled out and all that kind of stuff into this expanded format. We have to factor it. Okay? So that's kind of what I want to deal with here in section 3.3. We'll spend a couple days on this. This is not new to you. Okay, we're going to do long division of polynomials. That'll be the first thing we do today. Tomorrow we'll get into synthetic division, and hopefully the remainder in factor theorems tomorrow. Okay. Now, here's my argument to you. Okay. Long division. We are going to do a couple long division questions, but then for this particular topic, we're going to turn to synthetic division because it's more efficient. Okay. Now, when we turn to synthetic division, because the process is more concise and cleaner looking, we lose a little bit of information. Okay? We'll talk about that tomorrow. But down the road, when we start talking about rational functions, we start talking about a polynomial divided by a polynomial in a function format, we're going to have to do this long division again. So we're introducing it now, but it's going to be something that's pervasive through the next several chapters. Okay? So don't think, oh, Mr. Spencer, we're going to do 2 or 3 of these, be done, and I'm going to have to see this stuff again. It's going to come back. Okay? All right. So, dividing polynomials. I want to start with an explanation of 3rd grade division. Okay? 3rd grade division. If I have 38 and we divide by 7, okay? 38 is called the what?
Divisor. Dividend.
Okay. 7 is called the?
Factor. Yeah, I don't know. Quotient.
Divisor. Okay. The quotient is the result. And in this one, you're going to have a remainder, right? So here's the thing, and I want to kind of talk about what we call algorithms. Okay, algorithms are procedural things, and they're used a lot in like computer programming and stuff, that kind of stuff. You guys know, like when you get on social media and you see all these ads that pop up that are things that you have searched or talked about previously. Through your search histories or even your conversations with people, because Google's always listening, right?
Yeah.
You start to see things that you talked about or that you recently searched, right? They get your interest, okay? Well, there are algorithms that are written in the background that kind of process all this data that you're putting into these search fields, and it's coming up with things that are best aligned with your interest, okay? Algorithms are things that are kind of repetitive procedures, okay? When we did multiplication in 3rd grade, we did division in 3rd grade, these are called algorithms, okay? So, you guys learned probably, and I want to try to maybe contradict this a little bit or try to prove an easier technique. You tried to think about how many times 7 would go into 38, right? Okay. I think that's a terrible process. My thought, would you rather divide or would you rather multiply? What's easier? But which one's easier? Multiplying, right? Because multiplying is just adding multiple times, right? Repetitive addition. So, let's do multiplication instead. So the idea is, what can I multiply 7 by to get as close to 38 but less than 38? I don't want to go over, I want to be under it. 5. So I'm thinking about what can I multiply by this 7 to get something close to this 38. So then you multiply those together and you got 35, right? Yeah. Okay. Now what did you do next? Subtract it. I'm going to say you added the opposite. It'll make sense when we do an example here with long division or with polynomials. But what's 38 plus a negative 35? 3. Okay. Now the algorithm here told you to stop. The algorithm told you to stop here because that 3 is what compared to your divisor? Smaller. So our algorithm had a rule that says once your final line here is smaller than your divisor, you stop. That 3 becomes your remainder. And in 3rd grade, you wrote R3, right?
Correct.
Okay. I'm not going to write R3. I'm going to write plus 3 over 7. Okay? Now, the reason for that is because of what we did here with this 5. I took this 5 to multiply by 7 to get 35, right? If I take this 3/7, isn't that the number I need to multiply by 7 to get that 3? And now I can add the opposite of that, and I get to 0. Okay? So 5 plus 3/7. 5, let's identify these things. 5 is referred to as your quotient. 3 is your remainder. And in this format, 7 is your divisor again. Okay? But 5 plus 3/7, you guys know the mixed numbers, 5 3/7, right? 5 and 3/7 times 7 gives me 38. Okay? If we understood that, we should have no issues with something like this, dividing these things. And I'll show you this method right here. Because think about this. What are those things? What is X? What's X represent, Chuck? X represents a number. So let's say our number is 5. Let's say it's 6. So that would be 2, right? That would be 6 times 36 minus 26 times 36 plus 12. So I'm taking some pretty large number divided by 2 when I know what X is, right? So should the algorithm still be the same? Does that make sense? Okay. X is just a number. We don't know what it is. Okay. So, before we get into that, I want to talk about this here. Okay. It says that this is the division algorithm for polynomials. It says that P of X and D of X are polynomials. Okay. So that's the notation we use for just like an X squared plus 5X plus 12 and X minus 3 or something like that. Okay. We got 2 separate polynomials. It says D of X cannot be 0. Why can D of X not be 0? Because in the denominator, we're going to divide by a polynomial, and it can't divide by zeros. Okay? So then there exists a unique polynomial Q of X in R of X, where R of X is either 0 or degree less than the degree of D of X. Now, that phrase right there, so this is basically setting up the algorithm for us. Your remainder is either 0 or degree less than the degree of D of X. That is the rule that tells you when to stop doing your division. If your last line of work, after you kind of do your multiplication by your divisor, your quotient times your divisor, and you get a row, and you add the previous row to that row, and you get a result that is 0 or is of a degree less than your divisor, you stop. That's the idea that 3 was less than 7, so we stopped, right? Does that make sense? Okay. That's that rule for polynomials. So this is saying these are 2 formats that we're going to have to realize. It says P of X over D of X. So the quotient of 2 polynomials. Okay, that division is going to equal a quotient plus your remainder divided by the divisor. Is that what we had? We had 38 over 7. Does that turn into 5, which was my quotient, plus my remainder of 3 over 7? Does that make sense? Okay. Now think about this. They give me this thing over here, right? If I multiply everything over here by that denominator, d of x, does that d of x and that d of x cancel out? Leave me just p of x, which is that thing right there. Does that make sense? Okay. If I multiply the right-hand side by d of x, I have to distribute. So d of x times q of x, does that give me that right there? And if I take d of x times this here, don't the d of x's cancel out? And leave me just my remainder? Okay. So you're going to see in your homework, and this over the years has been something that people struggle with a lot in their homeworks. They're going to ask for that, and then maybe the next question, they ask for that. Okay? They ultimately for us say really the same thing. Okay? We got to realize what they're asking for. Pay attention to the directions. They'll tell you one of those two. Okay? So, in regards to our little example here, if I had 38 sevenths is equal to 5 plus 3 sevenths, they're saying that that could be 38. Basically multiply everything by that 7, right? So it'd be 38 is equal to 5 times 7 plus 3 sevenths times 7. Does that give me 38 equals 35 plus 3? You guys agree with that? Okay. So that is what those two highlighted arguments are saying to us. Okay. So I'm going to do an example of long division. But the idea is, if you could do 38 divided by 7, you ought to be able to do any one of these things that we do. Okay. Now I'm going to get rid of all this. Wish I had a better way to erase this. That's what I did. All right, so we want 6x squared minus 26x plus 12 divided by x minus 4. Okay? We can divide by any degree polynomial that we want to. So that x minus 4 does not have to be linear. Okay? And you might see some questions in your homework where it's an x squared minus 4, something like that. But the reason we're going to be using this algorithm in this application is because we're trying to find our linear factors of our polynomials. So we want to divide by things like x minus 4. We don't want to divide by x squared minus 2 or something like that. Okay? We want to try to divide by linear factors. So that's why a lot of the examples that you're going to see are of this. Okay? But don't get wigged out when this becomes like a 12th power here and this becomes a third power out there, because you do the same thing that we're going to do. Does that make sense? Mm-hmm. Okay. It's just for our next application of this, we want x minus 4 instead, x to the first minus 4. When we use synthetic division is going to require us to have x to the first minus 4. Synthetic division only works with division of linear factors. Okay, so the idea is, okay, remember, back when it was 38 and 7, I was thinking about what number can I multiply by 7 to get close to 38, right? So now here's the thing. This is a binomial. So when I think of a number, I need to multiply by that. Anything multiplied by that, any monomial multiplied by that is going to give me a binomial, right? So essentially what I'm trying to do is develop a number that I can multiply by x minus 4, or a term that can multiply by x minus 4. So it gives me something close to 6x squared minus 26x. but doesn't exceed that. Does that make sense? So the number one thing that we have to pay attention to that we're worried about is this term right there. That term is paramount. Okay? So we ask ourselves, well, what do I multiply this thing by so I can get a 6x squared? Blaze said 6x. Okay? Oh, man. There we go. All right, so we got 6x. And now, when that was a 5, we multiplied by a 7, we got a 38, right? But now it's 6x, so we got to multiply by the x minus 4. So 6x times x gives me 6x squared. 6x times negative 4 gives me negative 24x. Okay? You guys remember last year that if like that negative 26x was not there, so they said take 6x squared plus 12 and divide it by x minus 4, you had to put a placeholder in of 0x. Make sure you're paying attention to that. If you don't, you'll have like this negative 24x like lined up underneath the 12, and they're not going to be like terms to subtract. Does that make sense? Placeholders are to line like terms for us. Okay. When we did that, we took 5 times 7, we got 35, and we went 38 minus 35, right? So you can go 6x squared minus 26x minus 6x squared minus 24x. But I think that's problematic. Because a lot of people are going to say, well, 6x squared minus 6x squared, that's easy. That's going to give me 0. So let's just wipe away. But we get here, we get negative 26x minus negative 24x. What's negative 26x minus negative 24x? It's negative 2x, right? Okay. I don't like doing it that way because I get, one, it slows me down, okay, because I got to stop and think, okay, subtracting a negative means addition. So I know that that's the goal all the time is to subtract these, but is it adding the opposite, the same thing as subtraction? So I'll go through it, I'll negate every one of these terms in this new line, and then I'll add straight down. So those will wipe out. Now I get negative 26x plus 24x. In my mind, or visually, that's a little bit easier to do. Okay? Allows me to be quicker. So I get that. Now, do I stop or do I continue with the algorithm? Well, we've got to answer the question. These algorithms are repetitive things that you have to answer like a yes or no to either continue or to stop. Okay? The question we ask here is negative 2x plus 12, is it a degree 0 or less than, or is an amount 0, or is it a degree less than my divisor? What's the degree of negative 2x plus 12?
You can keep going.
I can keep going. It's degree 1, right? My divisor is degree 1. So I keep going. They're equivalent. So keep going. So what do I need to multiply then? So I just redo the algorithm. Now I'm thinking, what do I multiply x minus 4 by to get this thing? Negative 2. So negative 2 times x gives me negative 2x. Negative 2 times negative 4 gives me positive 8. Okay. I'm going to negate everything and add straight down. So those wipe away, and you're left with 4. Now, nobody's ever going to write this, so, I mean, you can write here in your notes if you want to, but this would be, come on. Can't change colors. That's actually x to the 0. Because x to the 0 is 1, right? So I have 4 times 1. Well, we just usually write that as 4. But this is why my algorithm stops here. Is that a degree less than the divisor? Yes. So it tells me to stop. So 4 must be my remainder. So I come up here, all right, plus 4 over the x minus 4 then. Okay. Now, if they were to ask to write my answer as, that clock's wrong. All right. We'll finish this up tomorrow, that stage. No